All right, continuing our talk about AC, not air conditioning, but alternating current. We are going to talk about point number 9. Number 9. Magnetic fields. That is Sally's cousin. Nobody in here knows who Sally Fields is anyway. So, all right, magnetic field in a wire. Sally Fields. Yes, actress. Smokey the Bandit.
Okay.
It is now. All right. In a circuit with no voltage, wait a minute. I'm just curious about it. In a circuit with no voltage, free electrons randomly move around. So there's electrons anyway, so they're going to move around, but they're kind of random. So they have no currents, they're not aligned, so they just float around. So you have this randomness of the electrons with their magnetic field, and it just cancels each other out. So I can put that. So in a circuit with no voltage, free electrons, I'm just going to say there is no magnetic field. That was much shorter and to the point. All right, when current flows, the electrons move in the same direction. This is where I need somebody to go, what? Wait? When did that happen? Move in the same direction. And their combined effort creates a magnetic field. Combined effort creates a magnetic field. This magnetic force then extends outside the wire. Beyond the wire, I should say. Outside and beyond the wire. So the magnetic field extends beyond. Magnetic force extends beyond the conductor. Oh, there's buttons on here. What does that do? Nothing. Magnetic force extends outside the conductor. This is going to be a very important point as we kind of continue on, especially when we get to magnetos. And actually, this, as voltage is increased, voltage is increased, well, the current also increases. Voltage is increased, current is increased. Current is increased. Current is increased, and the magnetic force increases. And the magnetic force increases. I'm just going to put left hand. Rule of thumb. I will not make you memorize the hand, left hand, right hand. Rule of thumb, I'll just tell you about it. So the force of the magnetic field is a left hand rule of thumb. You wrap your left hand around a conductor with the thumb pointing in direction of current flow. Fits for me, I'm busy. And then your fingers show the direction of the magnetic field. That's not really important. So you have a magnetic field that goes around. It doesn't really matter so much to me if it goes this way or that way, what we're talking about. So you just have to remember that that happens. All right. Simplify some of this. I'm going to talk about induced EMF. What's EMF stand for? Electromagnetic force, electromotive force. Let's see. Well, as we talked about with a generator, a wire moving through a magnetic field will produce EMF, voltage. So a wire moving through a magnetic field creates this voltage, which then causes current flow. So it doesn't matter if you have the wire moving through the magnet or the magnet moving through the wire. Whenever you have wire and magnetic field, the two of them have some sort of relative movement, you're going to create a voltage with a current flow within the conductor. Let's see. With DC voltage, the voltage goes, from 0 to max. When the voltage is max. I think I covered this yesterday pretty well. But if I don't write a bunch of stuff, I'm worried. Is it helpful when I write it? Mm-hmm. Okay. Then I will. I'll take the long road. I'm not going to save time, see world. As we talked about yesterday, we really wanted to write that. Talked about yesterday. Guess I could have left that part out. Yep. Oops. So I guess it's relevant that we talked about the generator yesterday, and it's like that. A wire moving through a magnetic field. A wire moving through a magnetic field will produce, I wrote voltage. Voltage / current, because you have one, you usually have the other. All right, with DC voltage, with DC, direct current, the voltage goes from, 0 volts to max, whatever the max may be of your battery, to max voltage instantly, nearly instantly, as opposed to AC where it has to build up to wherever the max is. You start at 0 and it kind of does the curve going up, or maybe you start down the bottom, it's got to go to the top. So with the battery, it's just boom, it's there, it's a straight line, it goes straight up and over. As long as current flows. We'll do that. When that's 3. All right. I feel like this one went ahead and went voltage. Nope, I'm going to do something different here. Hang on a second. This isn't in the notes, but I'm going to put it in there. Okay, so D goes from 0 to. So this creates. So I don't have a point here. This induced, I'm going to do that. Let me just tell you what I'm thinking, and we'll go with that. All right, so my next point that I would write down is when voltage reaches the max, counter EMF stops. But I haven't talked about counter EMF yet. It just kind of shows up here on my notes. I'm like, what the hell? So we have to talk about counter EMF. So counter EMF. So counter EMF. And I'm not sure how I want to write this. So when you have this voltage or this magnetic field building up in a wire, as that builds up in the wire, it creates a counter voltage to the voltage that's being applied. So counter EMF is voltage, voltage that induced voltage, induced voltage that opposes applied voltage. And this really comes into play with inductors, which is where this whole thing is going. So we just skip to inductors. So you have an inductor, a coil of wire, and as the voltage builds up, then so is the magnetic field in this wire is going to build up. So we have a straight wire, it's just going to build up in that straight wire. Well, when it built up, that voltage, the voltage started, and then the magnetic field starts in the wire, and that magnetic field expands out from a wire. There's a wire, and it kind of expands out from the wire. It didn't touch any other wires. So it had no effect on anything. Right? So you have magnetic field from the wire. But if I put another wire next to that wire, then, and I run the voltage through the yellow pencil, magnetic field's going to build up, and it's going to cut through the blue wire. Follow? And that would induce a voltage in this blue wire. It's just sitting next to it. It really does. Well, take a wire. Thankfully, I have one. I'm not using right now. And we have voltage going through it, and it expands, doesn't touch anything. But make a coil out of it. Thanks. Make a coil out of it, and when the voltage, keep saying that, when the magnetic field expands out of the wire, now it expands across the wire next to it, because I created a wire next to it. So it expands across that wire. Well, it induces a voltage in that wire, which is the same wire. So it's that voltage, and that's going to keep going. It's going to do it through all of these wires, and it sort of has an effect, accumulating effect on all of it. So now I've got voltage building up, through the wire, building up a magnetic field, cutting through the wire next to it. The wire next to it is really the same wire. So it is building up. It is creating voltage in the wire that has the voltage. Follow me so far? Yeah. But the voltage that gets created because of the magnetic field is backwards to the voltage that just went in it. So it's like I put a little battery in here, but I put the little battery in backwards. And so now it's pushing back this way. So that's counter EMF. And that's what happens with coils, is you get this counter EMF happens. So where am I here? So when voltage... in a DC circuit, though, right, when we close the switch, hope I don't ruin my wire here. When we close the switch on your DC circuit, we're going to have this buildup from 0 up to whatever we're using. We're using a 6-volt battery. Fine, then voltage goes to 6 volts. It expands out, and then it stops expanding because we're using DC. And now it's got the maximum amount of magnetic field. It goes 0, maximum, so maximum field. So it cut across it for a very brief second of time and then stopped cutting across it. Now we just have a magnetic field. So if I had a very strong magnet and I just put it in the magnet, what effect does the magnet actually have on the coil while it's just sitting there?
Little to none.
Little to none is correct. So what if I start moving it in the magnet?
You start getting a reading.
Now you do. So you got to have the relative movement. So again, DC, I turn on the circuit, boom, it expands. And during that expansion, there's counter EMF. But as soon as it builds up, there's no more counter EMF because there's no more relative movement. Well, guess what? When I open the switch, it's going to collapse. Magnetic field. The collapsing of the magnetic field is movement. So it's going to create voltage, current, wants to create current, which is going to oppose it collapsing. So in a coil, you have that issue where you apply the voltage and it's like, nope, stop. And then it builds up anyway, and then everybody's happy, and then you shut it off. It's like, don't stop, you got to stay. But it goes away.
So it's going to affect current?
Well, yeah, it's going to affect current because of that. But it's easier to talk about voltage right now. So then we'll get into the current. So we have that with DC. Now, let's take a look at AC. We have the same coil, and we turn on AC. Well, it builds up, and then it collapses, and it builds up, and it collapses. Well, it builds up, then it goes backwards, right? It goes all the way up, then 0, then backwards the other way, then 0, backwards the other way, and it never stops. So we have this magnetic field that is constantly, well, it's constantly doing this. and they go backwards. Yeah. So expands, collapses to zero, then it goes backwards, then it comes back to zero, then it goes forward, and so you have this constantly going on. So in a coil is this constant battle going on that never stops, which is what I wanted to talk about. So let me see, voltage.
Is there any relation to the shielded wires?
No.
Good answer.
Okay, I'll just go with what I got. So now that I've explained that, maybe see where I go. So point number 3, when voltage because I'm talking DC right here. So when voltage reaches the max, the counter EMF stops. That's CEMF, counter EMF. All right, with AC, now we'll talk about AC. With AC, the voltage is constantly changing. So is the current. Constantly changing, which builds and collapses.
You said the CMF stops?
When it reaches the max and just stops.
Oh, okay.
The DC.
Didn't write it.
So
Fair enough, I was
DC.
just trying to make sure I
Yep.
got the notes. Didn't write it.
Yep. With AC, the voltage is constantly changing, which builds and collapses. A magnetic field. Magnetic field around the wire. This creates an EMF that counters the flow of electrons. What does that sound like? Something that counters the flow of electrons or restricts voltage or resistance. It sounds like some sort of resistance, which is what it is. It's like resistance. All right, let's talk about Lenz's law. That was named after
Albert Lenz.
Albert Law. Yeah, you're so close. Lenz's law, as quoted, a change in current, a change in current produces an EMF whose direction is such that it opposes the change in current. Of course it does. A change in current produces an EMF so a change in current, we have AC, we have a change in current constantly. It's going up, it's going down, it's going up, it's going down. So that change in current produces a EMF, produces a voltage. So the change in current produces a voltage in the wire. Let me see. Produces EMF, whose direction is such that it opposes the, let me make sure I get it right, change in current. So the change in current produces a voltage that opposes the change that was happening. Follow? Which is why I was doing the ridiculous running back and forth with saying, all right, so the voltage starts to build up from this way. And I've got a coil of wire. and that produces a magnetic field around the wire that produces a voltage that says, stop, don't come back in, right? And so, but it does anyway. It just takes some time, and it builds up. And then if it was to stay up, you're like, you're here, whatever. Just might as well live and be happy. But it doesn't. It peaks out, and then it starts going the other way. The voltage starts because we switch directions, and now the coil's like, stop, don't go this way. Or actually, it's even worse because it builds up, and it opposes it, and then it starts to go away. It's like, don't go away. It's change again. It says, don't go away. Don't, just stay. And then it reverses direction, and it stops it from coming that way. So it's fighting it back and forth and back and forth. If the EMF added current, no, I'm not going to write this, which I suppose is a bad thing. Too bad it wasn't the other way around, because what if the EMF helped the current? I mean, that would be kind of cool. It's like, so then you get this buildup of magnetic field, which creates a voltage, which then causes more voltage, which then causes more voltage. And so really we could just get a little coil and power the whole world, right? But it doesn't work that way. We were so close, but then it just went the opposite. Yeah. Yeah. So if the EMF added current, it would cause runaway current flow. I'm not going to write that, but think about it. When current is increasing, the EMF opposes the increased current. I could write that because that's actually, so when current is increasing, the EMF opposes the increasing in current. And when current is decreasing, the EMF tries to keep the current from doing that. I should say counter EMF, really. Counter EMF, that makes more sense. Counter EMF tries to keep or opposes the decreasing current. The counter EMF is 180 degrees out of phase with applied voltage. Counter is 180 out of phase from applied voltage, which is to say it's just the complete opposite. So when you're peaking out on your voltage positive to negative, the counter EMF is peaking out down below. And when you're at zero, you're at zero.
And not to the applied current.
What's that?
And not to the applied current.
What do you mean? 180 degrees out of...
Because everything above is when you're talking about current change.
Yeah.
Okay.
Not sure I followed. Okay. Sorry. The amount of self-induced counter EMF is dependent and proportional on three things. One, frequency. So if change is a key factor, right? If we have DC, we have no change except for the on and the off. but AC produces this constant effect. Frequency is the number of cycles per second. Do you think more cycles per second is going to increase the problem or decrease the problem? More change equals more EMF, so therefore frequency, more change equals more EMF. Or counter EMF. Right? So the higher the frequency, the faster things are going to change. Faster it changes, the more relative movement you have. The more relative movement you have, the worse, the more it's going to induce a voltage counter to what you want in the coil. Therefore, the higher the frequency, the worse this problem. What was the other factor in creating this? Good. Current flow. Right, current flow. Takes current flow to create a magnetic field. If you don't have a magnetic field, you don't have a problem. You have a bigger magnetic field, then you have more counter EMF. So think about it. What created voltage to begin with? Yesterday we talked about. You had to have a wire and a magnet, and then you had to have relative motion. The faster the relative motion, the more current you would build up. The stronger the magnet, the more current. So what I'm saying here, frequency, the faster you move it, the more you're going to have. The stronger the magnet, the more you're going to have. Where does the magnet come from? It's electromagnet. So current flow. So current flow. More current, more EMF. Counter EMF. Also, the physical shape of the conductor. Is the conductor straight? Not so much. Straight conductor, counter EMF is just not going to really affect it. If it's coiled, then you're really going to have some issues going on there. Coiled, then you're going to have more counter EMF. EMF produced cuts through wires at multiple points. You could have one wire expanding out. This one wire expanding could be cutting across 3 or 4 wires. You know, so is it tightly wound? Is it loosely wound? What's the core? If it's got a soft iron core, then the magnetic field is going to build up in that soft wire core and transfer out. So let's see, EMF, multiple points. Straight, I'll just put that negligible. Counter EMF and coiled, more EMF.
If you have a bundle of straight wires running next to each other, would that
Can? Yeah.
affect each other?
Hmm? All right. As much as I don't want to go over this part because it's not exciting, it's important. The inductor as a coil of wire. So now we're going to introduce the term inductance. Inductance is defined as that property of an electrical circuit that tends to oppose any change of current through the circuit. So inductor is a coil. It's a coil. So inductance is that opposition to current flow. Like resistance, but it comes not from a resistor, but from a coil. All right, inductance is defined as that property, of an electrical circuit of an electrical circuit that tends to oppose any change of current through the circuit. It is a coil of wire. Coil of wire that may or may not be wound around a core. A coil of wire that may or may not be wound around a core. If you wind the wire around a core, it is going to have much different properties than if it is not. So core, especially if it's an iron core that has the ability to pass magnetic flux through it. So a core may be magnetic material. Which increases inductance. And magnetizes the core. Core doesn't have to be magnetic. It could be core. May also be, or maybe in lieu of, may be non-magnetic. Such as air or an insulator. Glass, something like that, which decreases inductance. So therefore, how much counter EMF, which is now called inductance for us, in this case, produced is determined by the core material. So if it's an iron core, we're going to get more inductance or less?
More.
Okay. Core material, the core size, number of turns, I would say the bigger the core, the more counter EMF. If you have a very small one, wouldn't make sense, wouldn't get a lot. Number of turns, a turn is simply how many times you went around something. How many coils you have. More coils, the more inductance. And size of wire. Lucky you. I crossed out this whole next half a page. All right. Just so you know, it is determined by the formula where L equals 0.4 pi n squared microamps divided by L, a little L. And number of turns, more inductance. Core permeability. Permeability is defined as the measure of ease which a magnetic flux can penetrate material. We'll talk about that next class. A is cross section, and L is the length of the core. A shorter core, more inductance. Thicker core, more inductance. More permeability, more inductance. So
Scroll up a bit. No, the other way up.
So
Thank you.
decimal 4 by pi.
don't write it. He was just complaining because I didn't write it. So I'm not going to hold you to this. I told you.
Cross it out.
Yeah. Sorry. I forget. Sometimes I'm talking and you guys are just writing. So, so I say really important things. And you're like, I don't know what he said because I'm busy writing, dude.
Yeah.
We'll have to figure that one out.
Is that over 2 or over L?
It doesn't
It
matter.
doesn't matter.
Well, I already wrote it.
It's an L. It's a little L
Oh.
because it's not the big L.
Is counter EMF a measurable thing?
Yeah, I don't know if you can measure it, calculate it.
Okay.
I'm sure somebody can measure it. But again, so everybody's with me now. So we can look at the formula, and the takeaway from the formula is the items that we just talked about: material, core size, number of turns, size of wire. So core material, if it's a magnetic, is that going to be more or less EMF, more inductance? More. Okay. More turns is more. More inductance. Yep. Permeability. What's permeability?
How malleable it is.
No, it's something's permeating it. Magnetic lines of flux. How
penetrable?
Yep. As the ease with which magnetic lines of flux can penetrate the material. Permeable. So these magnetic lines of flux can permeate the core. So if the lines of flux can do that, get into the core easily, we're going to get more inductance. All right. Some more permeability. If we have a thicker core, bigger core, we get more inductance. I'm just going more something. If we have a shorter core, you're going to get less. Okay. Inductance, spelled with an I, shown with an L, is measured in not amps, not ohms. Ohms is very close.
Henry's.
Yes. So inductance is measured in, I don't know if measured is the right word. I don't have a Henry's, maybe expressed as or measured in Henry's. Henrys. Henrys. Named after Joseph Henry, partner to Michael Faraday, who gets the honor of capacitance, farads. So capacitors are measured in farads. That comes from Michael Faraday. He gets the honor. Henry is defined as, let me see, a Henry.
Could have made it cooler, like Henry ads or something.
Is that Henry?
So you could have made it like Henry ads or something.
Henrads. Henry is defined as a conductor. A conductor has an inductance of 1 Henry if that, one Henry if a current that changes at a rate of 1 amp per second, 1 amp per second, produces a CEMF of 1 volt. There you go. So if current that changes at a rate of 1 amp per second, 1 amp, 2 amp, 3 amp, 4 amp, 5 amp, produces a counter EMF in this inductor of 1 volt. It's said to have 1 Henry. And I'm not going to do this part. Henry can be calculated by the formula CEMF equals negative L delta I over delta T, which is what I just kind of said. Delta is change. So we can skip that part. And you will be happy. Inductance in circuits. So inductance in circuits. This is actually 11, inductance. Sorry. You're going to hate this next part. I'll do my best. All right. I've already talked about all of this. This is kind of a review. I don't even know if I want to write it. Yes, you'll say, please write it. In a DC circuit, the only changes in current is when turn it on or off. So in DC, trying to abbreviate, save time, see world. In DC, what can I put? DC current only changes during on or off. Fair enough? Mm-hmm. So in a purely resistive circuit, what does purely resistive mean?
All resistance.
Kind of.
Volts and amps are in phase.
Well, let's talk about DC.
Oh,
What does it mean if it's purely resistive?
only load is a resistor.
Is what?
Only loads are resistors.
Only loads are resistors. Now that applies to AC or DC. So purely resistive means there's no coils, there's no inductors, there's no capacitors, just resistors. So in a purely resistive circuit, in a DC purely resistive circuit, this happens nearly instantaneously. This happens nearly instantly. What is that? The circuit turning on, the flow of amps from 0 to full. In a purely resistive circuit, nothing's opposing it. It's just boom, there it is, speed of light. So in a DC circuit with inductance, current, I'll say, no longer goes from 0 to max, max volts / current. There. I should have just said current. Makes more sense. DC circuit, I'm changing what I'm writing here. Current, okay, so in a DC circuit with inductance, current no longer goes from 0 to max current instantly, as it did with just resistors. Why does it not do it instantly when I add an inductor?
You're adding resistors.
Because
Now you're getting counter EMF.
I am adding resistance in the form of a coil, which causes counter EMF. So when I turn on the switch in a DC circuit that's got a coil, through the resistor, boom, instantly the current wants to flow. But it gets to the coil. Current flows to the coil. What happens to the coil, the wire? Magnetic flux builds up. That magnetic flux cuts across the wires that are coiled next to it. That magnetic flux moving, because it's building up, is relative motion across a wire, which causes counter EMF, which like dapping, I don't know, which opposes. So now it slows the current down. It's going to take a while for it to get through. So it's no longer instantly. And let me see. Yeah. So the greater inductance, the more henries, the longer that takes. It's like a commercial?
It's like inertia.
Oh, inertia. Yeah, because I didn't see how it was like a commercial. But inertia, yes. When I open the switch, the opposite happens. You open the switch, current wants to die down. If it's purely resistive, it goes away instantly. But now as it tries to die down, and the voltage goes away, and then the amperage starts to go away, it collapses the field. And as it collapses, we again have that magnetic field going back this way, which is relative movement across the coils of wire, which causes what?
Creates more voltage.
Creates more voltage. But it's the opposite of the collapse. So it keeps it from collapsing. So now it takes a while for it to fall off all the way. Follow? Yes? Okay. Am I hurting you? All right.
No.
We'll take a break.
I got married.